So today we have Yudai Suwa. So he's a researcher at Tokyo University in Japan, and he will be talking to us about his work. Very relevant for us with supernova neutrinos, including how to extract key parameters from the neutrino signal and using the upper limit from Super Kamiokande data for the particular source M31.
Okay, thank you for introduction. Hello, everybody. I'm Yudai Suwa from University of Tokyo. Today, first of all, I'd like to thank organizers for inviting me to present our recent work. Today, I will be talking about the possibility of quantitative analysis of the based on neutrino observation for stellar quark collapse. Okay, let me start. So first of all, I'd like to emphasize that the supernova is very nice candidate for multi-messenger observation. Because in order to understand supernova physics, we need four all fundamental interactions. So gravity is the most important part because total energy is how to say determined by gravity. And electromagnetic force is also important to describe the pulsar's magnitudes, which is left behind the supernova explosion. Weak interaction, this is the most important point, interaction in this talk because weak interactions are generating neutrinos. And strong interaction is also important to understand supernova because strong interaction describes the neutron star properties. And each interactions make different signals. From gravity, gravitational waves are emitted, and weak interaction makes neutrinos, as you know, and electromagnetic interactions are making the broadband electromagnetic waves, and strong interaction makes a neutron star. And also, a neutron star evolves, electromagnetic waves are again coming, and if the neutron star has binary companions, the binary neutron star merger can generate gravitational waves and electromagnetic waves. And if it's nearby, neutrino might be detected. So multi-messenger observation, with multi-messenger observation, we can look at supernova from different point of view. When we are looking at optical depths, the different signal have different optical depths. And when we are starting from the electromagnetic waves, it has a very strong coupling constant with matter, so the photosphere is pretty huge. And when we are looking at the deep inside, and there's a neutrinosphere, from this sphere, neutrinos are emitted, and when we are going even deeper from protoneutron star, the gravitational waves are emitted. And these three different signals have different interaction with matter, and there the virtue of the gravitational wave, because of its small interaction with matter, so it can escape from deep inside. Neutrino has only weak interaction, but still it has some interaction with matter, and there is less scattering surface. And so as the aspect of the detectability from bottom to top, in the top, that it's easy to detect. In the bottom, it's difficult to detect. But it's when we are looking at the escape fraction, the direction is completely opposite. So from electromagnetic wave, it's easy to detect, but it's too strong with coupling with matter. So neutrino is the best candidate because it mildly coupled with matter, but it's still not very difficult to detect. So that's the reason why in this talk I'm focusing on neutrino here. And first, let me start from the neutrino emission from supernova. That means neutron star formation case. Let me start from this object, supernova 1987A. Of course, we need to start from this object as when we are talking about the neutrinos. at that point, at that time, we could detect only roughly 20 neutrinos with the three different detectors. So this is a famous diagram. The horizontal axis is the time after first events, and the vertical axis is the energy of each event. And at the point, what we know is that the duration of the neutrino emission is about 12 seconds, several 10 seconds, and the typical energy of the neutrino detected at that time was about several 10 mega electron volt. That is all we know from this event. So let's think about how many neutrinos we can observe now. Based on these statistics, and when we are talking about neutrino detected by water Cherenkov detector, let's use this number based on the Kamiokande detector. At the time, from supernova 1987A with Kamiokande, there were 11 neutrinos, and Kamiokande has about 2 kiloton in volume, full volume. And distance was a little bit larger than galactic center. I mean, this object appeared in the Large Magellanic Cloud that is about 50 kiloparsec away from the Earth. And let's assume that now, if we have galactic supernova and the supernova takes place at the galactic center, then the distance should be about 8 kiloparsec, so roughly 6 times closer than 87A. And with Super K, the fluid volume is about 30 kiloton, and that means that 15 times larger in volume. Combining these two facts, larger volume, closer distance, then what we can expect from the 87A events number, that then from this configuration, we can expect 7,000 neutrino will be detected. But of course, this is based on this small statistics. There are huge statistical error, the 6,900 plus minus 2,100 event. That is expected based on this number. But of course, when we have a real event, this statistics should be much smaller because we have a much larger event number, then Poisson's error should be much smaller here. And let's assume that the hyperk is running, then volume becomes even larger, 200 to 20 kiloton. Then the expected event number based on this event number is about 5,000 event will be detected with hyperk. So based on these large statistics, we can do completely different science. And if we detect many neutrinos, we can extract many physical quantities. The first physical quantity is binding energy. Of course, it's very important for energetics. But actually, this was already done with supernova 1987A. And but unfortunately, this binding energy has a parameter, so some parameter degeneracy, because its binding energy is written like this. It's combination of the gravitational constant, mass, and radius of neutron star. By imposing this number, so neutron star mass being the 1.4 solar mass here, and the neutron star radius being the 10 kilometer here, then the total expected energy will be 10 to 53 x. It's large, but still it has some parameter degeneracy. So in order to do physics, we need to estimate mass and radius independently. So mass is important because in order to discriminate the final object, so neutron star or black hole, we need to estimate the mass. If this mass is smaller enough compared to the maximum mass of neutron star with the specific equation of state, we can expect within the supernova there is a neutron star. But if this number is too large, about let's say 3 solar mass, then the central object would be black hole. This is very important to say something about the final object. So radius is also important because in order to discriminate the nuclear equation of state, radius formation is pretty crucial because I will show you the later that once we can estimate a radius, we can say what nuclear equation of state is more realistic one not. So to do this kind of physics, we need to estimate a mass and radius independently. And the question is that if we can do this kind of physics or not. In order to answer this question, we are now building a new collaboration that is called a new LC collaboration within the in Japan. So far, we are publishing 7 papers, and the 2 more papers are under review. Okay, this number 9 was just accepted. It will be published soon, and number 8 is now under review. So if you are interested in our activity, please have a look at these papers. And there's a web page if you're interested in, but please Google New LC collaboration so you can find it. So our main target is the late cooling phase for the new supernova neutrinos. Because in the early phase here, it's about a couple of seconds after the core bounce. So there are many interesting physics, explosion mechanism, accretion on the proton neutron star, multidimensional effect, neutron oscillation, blah, 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 blah. Unfortunately, it's too complicated. So based on number of numerical simulations, still it's very model dependent. That means it's highly uncertain. When we are looking at the late phase, it becomes less uncertain because this kind of complicated physics are gone. The situation becomes much simpler. So let's say we need only 2 parameters. One is a neutron star mass, and next is a neutron star surface temperature. With these 2 numbers, we can calculate the lightness of the neutrinos and the time evolution. Sorry, please ignore this part. And when we are looking at the numerical results, here there's one example of the early phase neutrino luminosity evolution. So there are 3 different flavors are shown. And as you can see, it's highly flavor dependent. The black is an electron type neutrino, and blue is an anti-electron type neutrinos, and heavy leptonic neutrinos are shown as red. So it's highly flavor dependent. And also it's very complicated because it evolves flat here and some oscillation coming from the hydrodynamic instabilities and sudden drop because the accretion onto the proton neutron star becomes weaker, and then later on because of multidimensional effect, it's some constant luminosity epoch. So it's really complicated. When we are looking at a later phase here, about the several seconds after the core bounce, so these curves are really simple. So and also we can see the flavor dependence are already gone. So nu E and anti nu E have almost the same identical luminosity evolution. That means situation becomes much simpler, and we can say, okay, we can make some simpler model or analytic model within this time scale. This is what we are now doing. So in order to do that, we are dividing our work into 3 steps. In the first step, we performed a number of numerical simulations because we have only one real data of the supernova neutrino. I mean the supernova 1987A. This is only the data we have. But in order to understand the parameter dependence, we need more data. So in order to do that, we perform a number of numerical simulation to get a cooling curve of many proton neutron stars. And also here, we are now taking into account detailed physics But unfortunately, because of numerical simulation, we have only discrete grid of data sets. So in order to connect, or in order to broaden the parameter space, we derived an analytic solution here. And this analytic solution is based on the Boltzmann equation of neutrinos, but there are a couple of phenomenological parameters that are calibrated with the numerical simulation. This is our second step. In the third step, is based on the second step analytic solution, we develop the mock sampling code and also analysis pipeline code to make the quantitative data analysis based on the neutrino observation. This is our third step. Let me explain these three steps one by one. In the first step, we performed a number of numerical simulations of proton-neutron star cooling. So event rate evolution was calculated beyond 100 seconds. So this is the world's longest numerical data, which covers multiple neutrino light curve evolution with in systematic way. And we found that event rate evolution. So this is the event rate evolution about within 20 seconds here, and this is the event rate evolution beyond several 10 seconds. Both figures show that the luminosity evolution has highly correlated with proton-neutron star mass. That means, based on the luminosity evolution, event rate evolution, we can extract proton-neutron star mass independently with the binding energy. This is what we found based on the numerical simulation. In the second step, we derived the analytic solution. And here we solved the neutrino transport equation analytically. But of course, it's too very complicated. We need to import some assumptions, but these assumptions are physically motivated. That means, and also after deriving the analytic solution, we can judge the validity of our analytic solution with comparing with numerical simulation. So the neutron luminosity can be written like this simple function. So mass, proton-neutron star mass dependence, proton-neutron star radius dependence. This is a phenomenological parameter, and there are time evolution. And also we can derive the neutrino average energy like this: mass, radius, phenomenological parameter, and time evolution. And this is a comparison with an analytic solution with a numerical solution. So these gray lines here and here are luminosity evolution. This is luminosity evolution of numerical simulation, and this is the average energy evolution from the numerical simulation. Colored line are showing the analytic solution. But in order to fit the numerical simulation based on the analytic solution, we need two-component model. In the early cooling phase here, like this dotted line, dashed line, it has a beta equals 3. That means the mainly neutron star surfaces consist of the free proton and neutron. But as time goes on, the surface temperature is getting smaller, then nucleation takes place. That means the free proton and neutrons are combined into the heavy nuclei. And with heavy nuclei, coherent scattering boosts the optical depth, opacity cross-section. Then we need to take into account the boosting factor of the cross-section. That is the second component. Combining this early component consisting of free proton and neutron and late phase heavy nuclei, we can reproduce the neutrino luminosity evolution and average energy evolution simultaneously with this simple analytic solution. This is what we found in the second step. And based on the analytic solution, we can calculate the mock observational data. And so this is one example. Here we calculated neutrino scatter plot based on the time evolution, time and event energy. This is complete the same as this figure. this one. So time, event energy as function of time in this scatter plot. This is what we have in the time of the 1987. This would be changed once we have the galactic supernova, which is observed in super K. This kind of data will be taken in near future. This is what. Yeah. And also, based on this data, we can perform the parameter estimate based on the least square. This is a pretty simple data analysis method, but even though we can estimate proton neutron star mass, proton neutron star radius, and total energy independently. So this is a probability density function based on this mock data. So as you can see, so it's pretty accurate. Well, precision is pretty high. So the error is the uncertainty coming from the data analysis about 10% for even for the this kind of rough data analysis code. And also analysis code that is called special blends that is developed by the Akira Harada that is available on GitHub. So if you are interested, please check the special blend in GitHub repository. And so this is our first trial to finalize. Sorry, our first trial to develop the pipeline analysis code. That is third step here, but we have an extra bonus. Once we completed the data analysis code, we can do even more interesting thing. Here we developed we extended our pipeline code to estimate distance to a supernova, because this is analytic relationship with a proton neutron star radius, which can be written by the event rate here, positron average energy here, detector volume here, and distance. This is pretty simple analytic relationship. If we are interested, please look at this paper. We can explain what this relation is coming from based on the analytic model. Anyway, in this third step, we were assuming the distance is measured by the different observational method like optical or infrared telescope. But before this kind of electromagnetic wave is coming in, we need to estimate a distance with neutrino alone. And here we were checking if we can measure distance toward the supernova with neutrino alone or not. And here we found that we can estimate a distance toward the supernova within 15% of the 2 sigma uncertainties. And this distance estimate is possible because we know the neutron star radius by the NICE observation here. So X-ray telescope can measure the neutron star radius with about 10% statistical error. Then once we can put the proton neutron radius here, we can estimate distance and vice versa. So why distance estimate is important? So let's assume that we have the supernova takes place nearby. Then so far we know that from the neutrino observation, we have some angle information. If the for instance, if the super K is observing a number of neutrinos from the electron scattering event, we can estimate this direction of the neutrino observation, right? So the angle constraint that is well known based on the neutrino observation. But if we have distance constraint, we have different position constraint like this. combining angle constraint and distance constraint, we have the three-dimensional localization. If we are lucky, supernova candidate star might be identified before electromagnetic wave is coming in, right? If it's possible, we can perform the multi-messenger follow-up observation from the radio band to gamma ray band for the shock breakouts or the early light curve evolution. This is great. But in order to do that, angle constraint is not enough. With distance constraint, it's pretty important to get three-dimensional localization. That is the reason why distance constraint might be very important or interesting. And actually, this information can be used in two steps. So before finding supernova, neutrinos can tell us distance to supernova with 10% of statistical error. And then multi-messenger follow-up observation become possible with three-dimensional localization. And position determination is very important because multi-wavelength observation for some electromagnetic telescope has a very small field of view. So in order to observe the supernova before it takes place, the precise position determination is pretty essential. But if we have the large field of view telescope like the LSST, then we don't need the precise sky position. But when we want to use an X-ray telescope or radio telescope, which has small field of view, sky position is pretty crucial for the follow-up observation. So this because then the distance or direction information before finding supernova is pretty is essential for follow-up observation. After finding supernova, the story completely changes. Then let's suppose that distance is measured by optical or infrared observation with 1% uncertainties. Then we can use neutron data to measure neutron star radius with this high precision. And combining with mass estimate based on the neutron observation, we can put some constraint on the mass and radius relationship of neutron star. And this is the current constraint of the neutron star mass and radius relations. So radius of the neutron star mass as a function of radius. So there are a number of lines. So these lines are corresponding to different nuclear equation sets, that mean nuclear physics. But in order to figure out which equation states is more realistic, we need to put a stringent constraint on this plot. But unfortunately, the current constraint is pretty broad. Many possibilities are still remaining. So this is a gravitational wave observation. This is a nicer observation here, and this is a maximum mass observation of the massive neutron star. So all combined, even with combining all available data, we cannot figure out which is more realistic or not. So it's still a long way. But when we have the neutrino observation, the neutrino alone may be possible to put this kind of the very strong constraint. But of course, this is based on the analytic solution. We have some systematic error. So here we are taking into account only statistical error, but systematic error might make this error even larger. But it's also interesting direction to dig even deeper. Yeah. Okay, let me switch gear to a case of the black hole formation. So there was an interesting candidate of the black hole formation in M31 galaxy, so Andromeda galaxy, very nearby. And this is called M31 to 2014 DS1. So this mass signature disappears without making supernova. And the distance is nearby, within 1 megaparsec, so about 770 kiloparsec away from the Earth, the really nearby universe. And the light curve of this object this is the infrared light curve. So it's almost constant, but at some point it becomes dimmer and dimmer gradually. But when we are looking at the optical observation, these points, it has sudden drop here. And around these points, so after 2018, only the upper limit are put it. So maybe one single massive star disappeared up to this epoch. So based on the optical light curve, maybe around 2014 or 2016, there was something takes place, and maybe black hole formation took place at the center of this massive star. So let's think about what we can say based on this observation. And actually, black hole formation makes different neutron emission. This is well known. So this is one example. When we have the neutron star inside, the neutrino luminosity evolution will be like this. The neutronization burst, and maybe neutron luminosity is getting smaller and smaller as time goes on. But if the star is massive enough, maybe within very short period, the black hole will be formed, then neutron luminosity is increasing as a function of time because heavy accretion on the compact objects makes the proto-neutron star surface hotter and hotter. Then the neutron luminosity is getting larger, and simultaneously neutron average energy is also getting larger. Then expected neutron number is very much larger in the case of black hole formation than neutron star formation case. So that might be imposed in the neutrino spectrum. So this is one example of the neutron star, spectrum of the neutrinos as function of the energy here. So in the neutron star formation case, the spectrum cut off is about several 10 mega electron volt here. But when we have the black hole formation, then the spectrum becomes harder. I mean, larger energy neutrino will be expected once a black hole formed inside the star. So let's think about this specific object, whether we can expect a neutrino from this object or not. To compare with the observational data, we need to estimate how many neutrinos we can expect. And let's assume that inverse beta decay. Then the neutrino expected event number can be estimated like this. So detector volume here, M is the proton mass, Nu is the total energy emitted by neutrinos, and this distance, this average energy, and this is a cross section weighted by the spectrum. And when we assume the Andromeda distance toward the Andromeda galaxy here, and the average energy being 15 mega electron volt, and total energy emitted in the electron type neutrino being 10 to 53x, then the expected number of neutrino event will be about similar. So if we have this number, maybe we can detect neutrinos based at the time of the black hole formation time scale. So let's check whether we could detect the neutrinos at the time. And 2014 Super K was running, and they have published a vast search paper from the Super K collaboration, this paper. And by looking at the Super K collaboration paper, they have found nothing. So they tried 3 different time windows. So in the time window 1, they were looking for the 2 event cluster within 0.5 seconds here. And in the time window 2, they were looking for 2 events within 2 seconds. And in the third case, 4 events within 10 seconds. With these different event selection criterion, they found nothing. So maybe the large most possible detection number would be smaller than 2. Based on this constraint, we can make some constraints on the theoretical quantities. And in order to make in order to in order to compare the theoretical prediction with the observation constraint, we need to compile all available simulation data. So the oldest one was about 2005, 2007. And later on, there are a number of numerical simulations that are trying to make the black hole formation at some point. And here there are a number of numerical simulations. They have the different total energy emitted by neutrinos and the average energy here. So let's plot these numbers in this plot. I mean, in this parameter space. So this is the average energy of the new Ebert. And this is the total energy emitted as anti-electron type neutrinos. And these points are corresponding to the simulation data. And the difference of color are coming from the different equation state. So here there are a number of numerical simulation, but they are making use of the different progenitor model and different nuclear equation state and different gravity treatment. So, but here we found that equation state is the most important quantity to understand this figure. So black points are using the Shan TM1 equation states. It has a huge maximum mass of neutron star. Okay, please let me remind that the maximum mass of neutron star is dependent not only by nuclear equation state, but also by the finite temperature effect. Here, I'm using the finite temperature or finite entropy core to put the maximum mass of neutron star. So when we are looking at the cold nuclear equation state, then maximum mass of neutron star is the largest one is about 2.2 or 2.3 solar mass. But when we are talking about the thermal protoneutron star, protoneutron star has some contribution to make the pressure even larger than the cold equation state. Then maximum mass becomes larger than cold nuclear equation state. That's the reason why it is the 2.6 solar mass or 2.5 solar mass. This sounds too large if you were familiar with the nuclear equation state business, but these numbers are coming from the nuclear equation state with final temperature effect. So, and when we are looking at the points with deep color, they are larger in this plot because it takes time. Because the maximum mass is larger, that it takes time to make a black hole. So, in order to make a black hole, long period accretion onto a protoneutron star is needed. Then total energy of neutrinos are getting larger, and also hot protoneutron star is formed, average energy is also getting larger. That means larger expected neutrino event would be realized in the case of the Shan TM1 and Shan TM1E. And Latimer and Swift equation say this is also old equation state, but it's still broadly used. These guys had prompt black hole formation within very short time scale. Then the total energy of neutrino is not that large, and the spectrum is also not that hard. Then the expected event number is not that large. And these colored regions are a constraint coming from the observation. It's 99% rejection confidence interval and 95% here, 68%, 50%. So they are corresponding to the specific expected event number. So I mean, if the neutron non-detection is I'd say used to get some constraint, then this equation of state with a larger neutron stars would be rejected by the 95% of the confidence level. But most of the equation states are still not get constraint stringent. I mean, most of them are still surviving, even with the Andromeda galaxy. I mean, there's black hole formation candidate within Andromeda galaxy, so nearby galaxy. So, but anyway, this is physically physical. We can put some physical constraint based on the non-detection of neutrino by comparing a numerical simulation. And okay, and this is some example of the nuclear equation state as a function of the final temperature effect. We are plotting these four different equation state here, like this: the Latimer-Swesti, SFHL, Togashi, and Shan. So this monotonic, so this is Latimer-Swesti 180 to 20. Togashi, sorry. This is SFH. And this is Shen, H-Shen equation state. Togashi is here, sorry. Togashi is here. So it's some monotonic trends are also have some relationship with the neutrino observation here. Okay, it's almost time. Let me summarize. So now we are in a new era of the supernova neutrinos. So we can do quantitative analysis science. So and measuring key features mass, radius, and total energy of the proton neutron star. That it is measurable based on the neutrino observation alone. And now we are looking for the practical use of the neutrino supernova neutrinos. And at first we found that measuring distance of the supernova is possible, and also constraining the black hole formation is doable. But in order to improve the astronomy with neutrinos, so better pointing accuracy of the multi-messenger astronomy is important. And let's integrate the neutrinos with electromagnetic signals and gravitational waves that will provide a better understanding of supernovae. Okay, that's all. Thank you.
Thank you very much, Yudai. Any comments or questions?
I can start.
Yep.
Good.
Great talk, Yudai. Thanks.
Thank you.
I guess I'm wondering what you consider the biggest systematic uncertainty. So you had that figure of constraining the mass and the radius. What, when it comes to using neutrinos to do this, do you think is the largest systematic uncertainty?
The largest systematic uncertainty would be this one. So here, today I do not explain deeply, but G and beta, we have two different parameters. So G is coming from the density structure. I mean, here, in order to evaluate this analytic solution, we are assuming the Lane-Emden solution of the proton-neutron star structure. That means the n equal 1 solution for the Lane-Emden equation. This is the analytic solution for the proton-neutron star configuration. But of course, as you know, at surface, this solution is not accurate. I mean, below the saturation density, the adiabatic gamma would be 4-sat. That means the density structure is even steeper. This G factor is taking into account the difference of the Lane-Emden solution to the gamma being the 4-sat. And beta is also has some large uncertainty because this can change the opacity by factor of several. Then these two factors makes some systematic uncertainty. But in order to make these uncertainties precisely, we need to compare our analytic solution with a numerical solution. So that is the largest uncertainty based on the analytic solution. Is it answer for your question?
Yeah, I guess so. So I guess sorry, kids. those essentially you're fitting that formula is in order to get that constraint. You're not necessarily just looking at the total energy. You're fitting the formula. Okay, I get it.
Yeah, total energy is not that important here because this is just thermal emission. So that, I mean, the thermal emission, the 4 pi r square sigma t force, that is really simplified black body emission. Then the neutrino temperature and radius information is enough. So total energy just makes statistics, but without it, we can't make it for the radius of the nuclear equation state constant.
So, I mean, but you had this other formula there, and of course it's equation of state dependent, I guess, but you have the total binding energy of that neutron star that you have very well constrained. Could you also then
But
constrain that with the
in the here we are now we are focusing on the late neutrino emission. Then the proton neutron star contraction is already over. Then the situation becomes simpler. But if we are taking into account all time series of the neutron emission, neutron proton neutron contraction should be taken into account. This makes the situation much complicated. So at the moment, we cannot take into account the contraction of proton neutron star. That can be seen here. There is a shallow, steep rapid evolution of the neutron luminosity here. It cannot be reproduced by an analytic solution here because the proton neutron star contraction is not taken into account in the analytic solution. So in order to understand here. In order to use the total energy emitted by neutrinos, we need to take into account contraction.
Okay, thanks.
Yeah, thank you, Suwa-san. Yeah, sorry. I guess there are a couple of comments or a couple of questions in the chat. But if I might just I guess add to the first question, which was about I mean somewhat related to the first question, sorry, on the cold neutron stars. I was also just wondering what the effect of, say, rotation would be on the protoneutron star. Because especially if you're dealing with the later phase, it seems to me as if the accretion may actually be spinning up the body as well.
So here we are not taking into account rotation, and so your question is about.
Well, my question was a little bit more general, just about the effect of rotation. But Shantanu also has probably a more specific question about the use of the radius from nicer observations.
Yeah,
that's the first message. Yeah.
Yes. So nice observation is called neutron star, and here, so I'm interested in the proton neutron stars, but actually here I'm focusing on the late phase. That means several seconds after the supernova explosion. Then proton neutrons are contraction. Proton neutrons are contract from about 30 kilometers to the cold neutron star radius within this time scale. When we are looking at this late phase, let's say about 5 seconds after the explosion, then cold neutron star radius can be used for the typical number for the proton neutron star radius. So that's the reason why this analytic solution can be reproducing the numerical solution at this point. So then radius for cold neutron star radius can be used. And this is the answer for the Shantanu. And when you discover the analytical analysis supermodel, you said we need to consider some assumption to solve the Boltzmann transport equation. Yes, here. And here we are assuming the diffusion assumption. I mean, the neutrinos are energy equipartition with matter, and the diffusive process can transport a neutrino from inside to outside. These assumptions are used, but actually this is also used in the numerical simulation. But here, and also the time stationarity is assumed to derive the analytic solution at some specific time scale. That is what we are using. And also, general relativistic effect is not taken into account here. The Newtonian approximation is used. I think that's all. Yeah.
Thank you again for that. Sorry, this is Jeff, just in case. Yeah, since I didn't have my first name up. So yes, okay. So thanks for going through some of the assumptions that you have. I mean, it was interesting that, I guess rotation is not part of that. I guess I was also just thinking about this in the context of another version of the sort of mass distance relation, which maybe Evan was too modest to mention, because that was actually that's one of his papers about actually estimating the mass from some of the early neutrinos, which of course I guess we're expecting that there wouldn't be quite as much difference between the different models, I guess. Evan can probably explain this much better than I can, but I guess it would be interesting in some sense, maybe this is just a comment, to actually be able to take the distance measurement that you're talking about from the late phase, as well as the distance estimate from the early phase, and see if they agree, because this could be quite interesting.
Yeah, sure. Yeah, when we have that different distance estimation, and when they are consistent, we can convince the other communities, electromagnetic community, I guess. Yeah. So, but in order to do that, we need to develop the pretty fast pipeline analysis code to do it within very short time scale. So now I'm discussing with Super K people to involve our method into their code. So that might be interesting step toward next observation and nearby observation. Yes.
Great. Thank you.
Thank you.
Yep. Thank you. And maybe Santano, do you want to go through the two questions that you put in the chat?
Yeah. So I don't know if you can hear me, but this is just a general question. So I think Ruben will start taking data and will discover type 2 supernova also at large distances. So will, I think, time coincidence searches help in reducing background if someone wants to search in neutrino detectors? I don't know if anyone has looked at this. I mean, this is a more general question. I mean, not directly related to this talk, but I was just wondering.
You mean type 2 supernova in the nearby galaxy?
Yeah. I think Ruben, I forget what.
Yeah. But still, the nearby galaxies is already far away. I mean,
Okay.
Andromeda galaxy is very nearby. It's next large scale galaxy. But for the typical type 2 supernova, the nearest one would be several megaparsec away. So then the neutrino, detecting neutrino is a very hard task. Maybe the expected event number will be 0.01 or something like that.
Okay.
Yeah, Ruben is expecting to see something like 1 million supernova a year, but that's a much larger distance. Also, just related to that.
Even in the Andromeda galaxy, for the typical type 2 supernova, it's pretty difficult to detect multiple neutrinos, because even for the case of the black hole, so in the black hole case, the expected event number will be larger than supernova case, but we cannot make very stringent constraint yet. So this is our current status.
But maybe to conclude on his comment. Of course, that having an electromagnetic observation with a proper distance will, even if we have only 1-2 candidates for Andromeda, allow to reduce the background and to know that those are actually true IVDs from a candidate and not background by applying the time correlation with even distance and position correlation with what electromagnetic observations can tell us. But yeah, I think we, as it was already mentioned, so far away we are not very sensitive, and only looking at through sub-threshold data and combining different experiments, maybe we can do something.
Yeah, could be.
in the
Yes, that's
future.
true. That's true. Yeah. But here, so I'm in this plot, I'm really employing the simplified assumptions. There's no energy cut and no selection bias for the event. So then maybe this my constraint is the expected event number will be overestimated. Once we take into account some energy cut or the spallation cut, then the expected event number will be smaller, then the constraint gets looser, I guess. But a more realistic data analysis is needed. Yeah, sorry.
Okay, thank you. So Slok also had a question on the chat.
Thank you so much for the talk.
Thank you.
Actually, I wanted to know when I discussed about the analytic solution for supernova production from Corco Labs. You said that we have to solve the Boltzmann transport equation, but we also need to make some assumptions for that. So what are these assumptions like? Are they related to some of the physical parameters that we're trying to measure? Something like that?
So for the Boltzmann equation, there are 7-dimensional different integral equation. But here I'm assuming the neutrino spectrum is Fermi-Dirac, and also diffusion process transports neutrino from inside to outside, and the gray atmosphere is used. That's it basically. And it's a normal physical assumption to make the equation simpler.
Okay, so does it reduce the number of equations that we need to bother about? Oh, okay.
And finally, we can derive that kind of the assumptions are used for the photon transport. Here I'm just using this kind of the normal astronomical assumptions to make the equation simpler. Yeah.
Okay, cool. Thank you so much.
Thank you. Any other question?
Yeah, otherwise, if there are no more comments or questions, that was very nice talk. It's already the 1 hour that we usually schedule. So yeah, I don't know if there are anything else to discuss on our side before we close the meeting.
Thank you.
Thank you.